Good evening and welcome everybody. It's OE1 Pez 4 and Simplex Pachinko. We are going to be working at some mathy type stuff tonight. So we're looking currently at where we left off on spherical geometry. This was our arXiv article. And boop. If anybody wants to follow along there, feel free. Full title, let's see. Can we do 2, 3, 4, 5, 6, 7? Yeah, cool. Alright. This was Euler's work on spherical geometry and overview with comments. Atanas Papadopoulos and Vladimir Turayev, November of 2025. Right. So Euler's other memoirs in Euclidean geometry mentioned here. In the latter, he proves several elementary results, including involving perimeter area and radius of inscribed circles and other characteristics of Euclidean figures. For example, one result says that if the area of a Euclidean rectangle is equal to the product of half the sum of its side lengths, with the radius. Oops, sorry, that's a statement, not a question, not a conditional. The area of a Euclidean rectangle is equal to the product of half the sum of its side lengths with the radii of the inscribed circle. Radius. In the memoir Solutio Problematis Geometrici, Solution of a Problem on Geometry, Euler represents his solution to another problem of Pappus, namely the two conjugate diameters of an ellipse, to find the conjugate axes. This problem is also quoted in T.L. Heath's History of Greek Mathematics. Talking of Heath, let us also point out a note in his edition of Euclid's Elements, in which he quotes the following theorem of Euler. In any quadrilateral, the sum of the squares on the sides is equal to the sum of the squares on the diagonals and 4 times the square on the line adjoining the middle points of the diagonals. Euler published several other elementary but not necessarily easily proven results on Euclidean geometry, and it would be interesting to work out the analogous systems on a sphere and in hyperbolic plane. All right. So, geography, astronomy, and geomagnetism being, I'm going to guess here, 3 of the most common applications for spherical geometry. Okay, yeah, literally the first line. You know, that's a very good question. You know what, Zach? I'm not sure we have the weights anywhere. They're not in here. But I'll do you one basically the same. I will hoist a box. This is books. So, hope everybody's having a good day. God. And you can hear them moving around too, so you know I'm not lying about it. So, okay, hang on one second. I got something in my eye. That's pretty fun too. Anyway, nope, that is off balance. There we go. Let's also do some squats with the box. Just so you can have weights, yeah. Yep, that is the problem at the moment. I believe they were taken into the playroom and or my son's room because he's been like, oh, I want to lift some weights. I'm like, all right. Can't even lift your 15-pounders all that well, but you know what? Go for it. He's not even 10. I give him a break. Yeah. That's fine. That's probably good enough. Yeah, yep. There's yeah, Feynman lectures are in here. In addition to most of my hey, tensor calculus. In addition to most of my other textbooks. Nice. Alright, that all goes on the bottom shelf. While we have it out. Physics. And math. Mostly PDEs. There we go. And the Kresek book, which is the Advanced Engineering Mathematics. This is the one that held the we use this in the prerequisite class that was partial differential equation, or no, sorry, ordinary differential equations, partial derivatives, and linear algebra. So it was a linearity course. This one was at grad school. So we ended up using that to essentially it was a pseudo-remedial class. Mostly meant for people who hadn't taken those classes in like computer science or physics or engineering, if they didn't need to take all three, or if they didn't do so well. Then they would be able to take this one class and satisfy all three of those prerequisites and say, yeah, you're good. Because, hey, if you could do all three of those classes in one semester, you must have at least satisfied the requirements at some point in your undergrad. Yeah, that was the class I got mono in during the second semester, so I ended up getting a D the first time around and a C the second time around a year later. So it was a little rough. Oh, you've got that one too? Nice. 1,000 points. Well, you know, Zach, the problem with that is that I did put a cooldown on it. It may even have a per person cooldown. I know. Boo. Boo hiss. Bad Obi. Very true. But you've got plenty of other ways to torture me. Oh. Said that out loud. Charles writes in Aperçu historique. That's what good form is for. I don't have space anymore for that. Good news, I can still do some Tai Chi. I can still do some karate in theory. I just can't actually do real forms anymore. I need to put the office in the playroom, which is the one that's like basically the same width as this room, which is roughly speaking 4 meters, just about. But it's like 8 meters long. It would be wonderful if I could put my office in there. But again, in that case, I would probably have to share it again. Apostle historique, that since the works of the ancients, he mentions Theodosius, Menelaus, and Ptolemy, if the theory of spherical geometry was extended and if it has attained in the hands of our most celebrated geometers a high degree of perfection, this was always done by almost preserving the same framework, because the goal was always the same: the computation of triangles in order to fit the service of the astronomer and the navigator, and for the great geodesic operations which showed the true form of Earth. Euler was interested in all domains of applications of mathematics, in particular geography, astronomy, and geomagnetism, which all involve spherical geometry. As already noted in section 3, Euler, in his memoir Principe de la trigonométrie sphérique tiré de la méthode des plus grandes et plus petites, used geographical terminology while he established his trigonometric formulae. In the introduction to his memoir, he talks about using the same methods for the study of the spheroid, the surface of the Earth being not spherical but spheroidal, and announcing his forthcoming memoir, Éléments de la trigonométrie sphéroïdique tirée de la méthode des plus grands et plus petits, in which he establishes by the same methods the trigonometric formulae for the surface of the spheroid, and from which he deduces explicit distances between certain locations on the Earth. The main question in the problem of drawing geographical maps is to find maps of least distortion, with appropriate meaning for this word, from a subset of the sphere into the plane. The volume contains memoirs by Euler, Lagrange, Lambert on this theory, translated into English and with commentaries. In Euler's memoirs on the subject, the geometry of the sphere, and in particular spherical geometry, trigonometry, plays a major role. Astronomy is also linked to spherical geometry because the celestial vault is assimilated to a sphere, and making the map of the sky and studying the movements of the stars amount to questions of spherical geometry. In any case, Euler's memoirs on astronomy involve some amount of spherical trig. For example, Memoir Solution Problématique, that is not French, that must be Latin. Solutio Problematis Astronomici ex datis tribus stelae fixae altitudinibus et temporum differentis tiis invenire elevationem poli et declinationem stellae. Solution to the problems of astronomy: given the altitudes and time differences for 3 fixed stars, to find the elevation of the pole and declination of the star. Published long before his memoirs in spherical trigonometry, consists almost entirely of considerations of spherical trigonometry, with some numerical examples in the last part. The goal of this memoir is to solve the problem announced in the title. Euler starts by recalling the following result, in which he attributes to Friedrich Christoph Meyer: in any spherical triangle ABC, we have the cosine of A is equal to cosine BC minus cosine AB times cosine AC all over sine AB times sine AC. He then proves the following statement, quoted as a theorem. In any spherical triangle ABC, we have cosine BC is equal to, same deal here, so we're multiplying that across, make it cosine A times sine AB sine AC. Nope, because this is all in cosines. Ooh, interesting. So that could be, yeah, that could be done by sum and difference of angles. So that could be a big pain in the rear. Yay. Likewise, the memoir De Inventione Longitudinis Locorum ex observata Lunae distantia a quadam stella fixa cognita. On finding the longitude of a star, longitude of a place by observing the distance between the moon and a known fixed star. Contains a substantial part on spherical trigonometry. There are many other examples. How would you find longitude? Okay, so presumably you're finding the angle between the moon and a known fixed star, and then determining what time of the lunar cycle it is, and then trying to compare what time GMT or whatever you would expect the moon to be at that place. Well, if you did that, all you need is the angle. All you'd need is the elevation of the moon. You wouldn't need to know where it is compared to a fixed star. Yeah, I don't know. If anybody can think of a reason, let me know. Contains a substantial part on spherical trigonometry. There are many other examples. On geomagnetism, we mention Euler's memoir Recherche sur la déclination à l'aiguille aimantée. Researches on the declination of the magnetized needle. Aiguille? Aiguille? I don't remember that. I guess we never really studied, like, what's a needle in French. The magnetic declination at a given point of the Earth's surface is the angle between the magnetic north and true north. In this memoir, Euler mentions the work of Edmund Halley, who proposed a new idea for showing declination on geographical maps, see 56. The memoir 28 starts with the following. Since this research, as well as the following ones, requires the analytical resolution of spherical triangles, it will be good to put the formulae before our eyes so that we do not need to look for them elsewhere. I will therefore begin with right triangles, etc. The memoir, which is 77 pages long, contains a complete set of formulae of spherical trigonometry without proofs that are used all along. Finally, let us mention that spherical geometry is the basis of an argument that is the subject of a letter sent by Euler to Maupertuis, dated July 4th, 1744. The argument is analyzed in Chapter 4, titled On the Duration of the Passage of a Star from the Almucantar to Another. From an Almucantar to another. Okay, so Almucantar must be one of the Arabic words that was borrowed into stellar cartography, essentially. We're going to look that one up. Nope. Okay, it probably is origin. A circle on the celestial sphere parallel to the horizon. Oh, okay. So it's the line. It's not a line on a sphere. Right. So it's the circle, which creates a cap with the North Pole at its top. Interesting. Haven't heard of that word before. Almacantar staff is an instrument chiefly used to determine the time of sunrise and sunset in order to find the amplitude of, consequently, the variations of the compass. Usually made of pear tree or boxwood with an arch of 15 to 30 degrees, it is an example of a backstaff. Solar almacantar. Almacantar plane that contains the sun is used to characterize multiple scattering of aerosols. Measurements are carried out rapidly at several angles at both sides of the sun using spectroradiometer and photometer. There are several models to obtain aerosol properties from the solar almacantar. The most relevant were developed by Oleg Dubovik, used in NASA Aeronet network. Really? Of course not. No, I'm sorry. That information is locked behind No. In Middle English period, earliest known use, between 1150 and 1500. Thanks. Geoffrey Chaucer, poet and administrator. Yeah, you're not going to go there, are you? Yeah, there you go. Almocantra. Yeah, exactly. Jerks. All right. Friedrich Christoph Meyer, 1762 to 1841, was a mathematician who, like Euler, was working at the Imperial Academy of Sciences in St. Petersburg. From the time of Euler's arrival to this academy in 1727, Meyer helped him with various problems of celestial mechanics applied to determination of the sun's orbit, movement of the planets, and calculation of lunar eclipses. In addition, Meyer worked with Jakob Heilmann and Daniel Bernoulli, we know that guy, on a theory of the moon based on Delisle's extensive program of astronomical observation, which included the occultations of stars and planets by the moon, as well as lunar and solar eclipses. At the time, Delisle was the major astronomer and geographer of the Academy. Daniel Bernoulli, I believe the fourth, is, as far as I know currently, in Basel, in Switzerland, and is a economist. Or at least 20 years ago he was. Oh, God, that's an old documentary. Okay, works mentioned in this section are not on spherical geometry, but we have collected them here because they involve the sphere, curves on the sphere, spheroid, etc. Indeed, Euler studies these memoirs in these memoirs, curves on a sphere embedded in the three-dimensional Euclidean space. In the memoir, De curva rectificabili in superficie spherica, on Rectifiable curves on the surface of the sphere. 1771. Euler studies curves on the sphere that are expressible by algebraic equations. He says that this problem arises from what he calls the Great Florentine problem raised on spherical surface a century ago. 1670s. He finds such a curve, namely the spherical epicycloid, obtained by the motion of a great circle on a small circle, whose diameter makes a rational ratio with the diameter of the sphere. From this question regarding the surface of the sphere, he moves on to more general surfaces. In the memoir Delineis rectificabilibus in superficie spheroidica quacunque geometries descendis, on rectifiable lines that have been drawn geometrically on a spheroidal surface. Published the same year, Euler gives a simpler proof of the result of the preceding one, at the same time generalizing it from the case of the sphere to the case of the spheroid. In the introduction, he points out the difficulty of the question of drawing geometrically algebraic lines on a surface, writing, "A most difficult question is when it is required to draw geometrically lines on a surface of any body with all of whose arcs defined algebraically, since in cylinders, besides straight lines parallel to the axis, no other rectifiable curves can be drawn." On the memoir De curvis rectificabilibus in superficie coni recti descendis, rectifiable curves drawn on the surface of a right cone, published in 1781, Euler finds a family of rectifiable curves on a right cone whose ratio of side length to the diameter of the base is rational. Let us quote from the introduction. Since we can certainly affirm that no rectifiable line can be drawn on the cylindrical surface except the straight lines themselves parallel to the axis of the cylinder, the same seems to be true of conical surfaces, because a cylinder can be viewed as sort of a cone, while the height is increased indefinitely. However, I have observed that there are such right cones on the surface of which, in addition to the straight lines drawn from the vertex of the cone to the circumference of the base, innumerable other curved lines can be geometrically described, omitting rectifications, but this does not seem to be possible on all right cones, much less oblique ones. Euler calls these curves rectifiable, a word used today in a different meaning. Rectifiable mostly meaning, well, having like electrical sense for quite a bit. I don't know what we would call it, or how we would define it, I suppose. Another problem on spheres. In this section, we consider Euler's memoir Solutio facilis problematis quaeritur sphera que datas quator spheras utcunque dispositas contingat. An easy solution to the problem of finding a sphere that touches four given spheres arranged in an arbitrary way. This is like a three-dimensional analog of the famous Apollonius's problem in the plane. Like the problems considered in the preceding section, strictly speaking, Euler's memoir is not on spherical geometry. Nevertheless, it concerns spheres. Euler presents two solutions to the problem of constructing a sphere that is tangent to four given spheres. The proofs rely on trigonometric formulae. Toward the end of this memoir, Euler begins using astrological signs as variables. Oh no. At the end of the memoir, Euler writes, "In this way we find a pair of solutions to a very difficult problem, which at first sight seem to require the most abstruse stereometric investigations, problems of this kind usually requiring both the most intricate figures and the most troublesome calculations, while the solutions here can be obtained with the help of not too lengthy calculations. The problem itself is not new. Once it was found to have been solved by the great geometer Fermat, but since at the time the calculation of angles was almost completely unknown, it is not surprising that our solution is found to be much more convenient." Yet another thing that Fermat claimed to have done. No. It is fair. He probably did solve it, but not nicely. There is a relationship between the two-dimensional Apollonius problem, which is at the origin of the problem discussed in this memoir, and the problem of Pappus, which is considered by Euler in the memoir and on which we commented in section 6. Guillaume Terray mentions this relationship in his commentary on Euler's memoir, chapter 4 of this volume. The reconstruction of Apollonius' proof, and more generally the work on this problem, attracted the attention of the greatest geometers such as Viette, Descartes, Newton, Poncelet, Gergonne, Cauchy, and as we said, Euler in his memo Solutio Facilis Problematis. The three-dimensional version treated by Euler in this memoir was also considered by Fermat in his De Contactibus Sphericis. On this higher dimensional Apollonius problem, besides Euler's memoir, we mention the works of Carnot, Hachette, Binet, Battaglini, Francais, Dupin, Serret, Coqueret, and Alvord. Chalais, in his Aperçu Histoire sur l'origine et développement des méthodes en géométrie, writes about Euler's work on the three-dimensional Apollonius problem. The question of a sphere tangent to four others is one in which geometry has long had the upper hand over analysis. In 1779, Euler presented his two analytical solutions of it to the Academy of Petersburg, which did not appear until the beginning of this century. In the volume of Academy for the years 1807-1808, printed in 1810, Carnot had already indicated an analytical solution in Géométrie de Position, but without carrying out the developments that would have led to a second-degree equation. Today it is Monsieur Poisson who was the first to completely resolve this question by calculation. En Bulletin de la Société Informatique. Shortly afterwards, Messieurs Binet and Francais also gave different analytical solutions in the 17th issue of the Journal de l'École Polytechnique and Tome 3 of the Annales des Mathématiques. This being the plate in which Euler used star signs for various variables. The reference to Apollonius is Apollonius of Perga, 262 to 190 BCE. Problem in its simplest form is to construct, using straightedge and compass, the circle that is tangent to three given circles in a plane. Apollonius' problem is part of his work Epaphai, contacts, or tangencies, which does not survive but is reported on by Pappus in his collection. Detailed content of what is known about the work of Apollonius and Epaphai. Nuts. I didn't study enough Greek. I don't know what all the diacriticals are. which does not survive but is reported on by Pappus in collection. Detailed content of what is known about this work of Apollonius and a history of the attempts made for its reconstruction are given by Weils, the Belgian editor of Pappus's collection. See introduction. We learn from there that Apollonius' work on this problem presumably contained 21 lemmas, 60 theorems, and 11 problems, which Pappus in his collection summarizes in a unique proposition, saying that given 3 arbitrary elements, which could be points, lines, or circles, to construct a circle which passes by the points, in the case where objects are circles, or is tangent to the lines or circles. Pappus enumerates 10 cases in which Apollonius solved the problem. Lambert used these signs on his memoir on taxonometry. See chapter 6 of the present volume. Figure reproduced there. Naturally, Apollonius' problem in the plane has been extended to a similar problem on the sphere and on other quadratic surfaces. The question on the sphere is to construct all spherical circles that are tangent to 3 given circles. To conclude this section, let us say that Euler has studied the classical two-dimensional Apollonius problem in his memoir Solutio Facilis Problematis, an easy solution of a problem in which a circle is searched for tangent to 3 given circles, written in 1779, published 1810. That's quite a lag time on that one. 31 years, jeez. This problem was generalized to the case of n greater than 3 circles, and to the case where some of the circles are replaced by lines or conics, to the case of intersecting circles, etc. There is a very large bibliography on generalized Apollonius problems. Among the mathematicians who worked on it, we mention again Pappus, Descartes, Newton, Gauss, Cauchy, Poncelet, Gergonne, Laguerre, and many others. Jean-Alfred Serret, in his paper De la sphère tangente à 4 sphères données, on the sphere tangent to 4 given spheres, solves the problem of the sphere tangent to 4 given spheres using the notion of power of a point with respect to a sphere. The square of the distance from the center minus the square of the radius. Gaston Darboux, in his paper Sur les relations entre les groupes de points, de cercles et de sphères dans le plan et dans l'espace, on the relationships between groups of points, circles, and spheres in the plane and space, solves the problem of constructing a circle intersecting 3 given circles at given angles. In his paper, Darboux says that the problem has been proposed by Jakob Steiner. Among the modern works around generalized Apollonius problems, we cannot help but think of the theorem of Kuber, Andreev, Thurston, review, blah, blah, blah. Finally, talking about Euler's work on spherical geometry, we should mention the works on this topic done by the young mathematicians of the St. Petersburg Academy of Sciences who worked under his direction or were inspired by him. We have devoted a forthcoming volume to this subject. The first author, has also published a short overview of this topic. Nuts. I meant to go over to the old house today. They've got their recycling today. Well, curses. Nope, not a tab. Just, there we go. André et Simon V. Mathematics, Social Activism, and Indian Culture. Athanase Papadopoulos and Sumusu Tanabe. November 26, 2025. This is an essay on the relation of André and Simone Weil with Indian culture and Sanskrit literature, especially the Bhagavad Gita, Hindu scripture, which they knew well, which they quoted extensively, and which guided them in making important life decisions. In addressing this question, we also talk about the life paths of the two Weil, and more specifically about certain aspects that relate to their deep convictions. A final version of this article will appear in the Handbook of the Mathematics of Arts and Sciences, new edition, edited Sriraman and Springer, 2026. André Weil is known in the mathematical community as a major figure of the 20th century. His sister, Simone Weil, was a philosopher and mystic, and is much better known than he is in the general cultural world. In this article, we focus on André Simone Weil's affinity with Indian culture and Sanskrit literature, which they had an especially close relationship, in particular the Bhagavad Gita, which they knew well and quoted extensively. It's word for word is some of that stuff in the abstract, and for which they expressed a true devotion. We shall address the question of how reading this Hindu scripture was linked with their intimate convictions and important decisions they made in their lives. Before we do so, however, it is necessary to properly situate André and Simone, both in relation to each other and within society in which their lives evolved. André Weil was born in Paris, 6th of May 1906, died in Princeton, 6th of August 1998. Several written sources of information will perpetuate his memory. His own wide-ranging writings contain an extensive record of his life and work and will help preserving them in cultural memory. Help to preserve, I would say. Among these writings we mention especially his reflections on mathematics and the history of mathematics, the commentaries on his works that he wrote for his Œuvres Scientifiques, collected papers, published in 2 volumes by Springer, his autobiography Souvenirs d'apprentissage, translated into English under the title The Apprenticeship of a Mathematician, his correspondence with his family, and especially his sister, published by Gallimard in Volume 1 of Tome 7 of the latter's complete works, and his correspondence with mathematicians, in particular with Henri Cartan. There are numerous tributes to him written by colleagues who had known him and were familiar with his work, including Borel, Cartan, Cartier, Ianaga, Serra, Shimura, and others. See also the reports by Pekonen and Varadarajan. Another important source of information on André is the biography of his sister Simone, written by her friend Simone Pétremont, which gives an affectionate picture of the family and intellectual atmosphere in which the two Weil, André and Simone, grew up. Finally, let us mention the novel by André Weil's daughter Sylvie Weil, titled Chez les Weil, André et Simone, with an English translation titled At Home with André and Simone Weil. The novel is about Sylvie Weil's family, in particular her father and her aunt Simone, who are our main 2 subjects in this article. There's probably no need to introduce André Weil to a mathematician reading this article. Yeah. Let us only recall that he is the main founder of the Bourbaki group, and that his name is attached to a number of objects and theorems that had a profound and durable influence on mathematics, including, among which we mention the Weil-Patterson-Kada metric on Tishmula space, the Durham-Weil theorem in algebraic topology, the Chern-Weil homomorphism in the theory of characteristic classes, the Taniyama-Shimura-Weil conjecture in number theory, a conjecture which became later the modularity theorem, of which the Fermat-Last theorem is a special case, and Weil conjectures on zeta functions in the theory of algebraic varieties over finite fields, conjectures that have had a considerable influence on the foundations of modern algebraic geometry. There are several other mathematical concepts called after André Weil, named after. Simon Pétremont, 1907 to 1992, was a French philosopher and essayist who had been Simone Weil's classmate at Lycée Henri IV and at the École Normale Supérieure. Pétremont was one of the first 3 women to enroll at the literature section of École Normale. It was to her that the Weil parents entrusted the task of writing their daughter's biography, and that André Weil confided in his recollections of his sister. The biography she wrote, La vie de Simone Weil, was awarded a prize by the Académie Française. Cartier, in number 7, writes, Bourbaki was undoubtedly Weil's creation, even if there was no shortage of strong personalities. In this article, all the translations from the French are ours except when the official translation is indicated in the bibliography. In this article, we shall talk about André Simon's attachment to India and Indian culture. Since we started the article by talking about André Weil, let us mention here that he spent 2 years in India, 1930 to 32, teaching at Aligarh Muslim University. It is interesting to know how he came to hold this position, since it is related to the heart of our subject here, and we shall say a few words on this. André Weil writes in his apprenticeship that at the time he was working for his doctorate, he was highly attracted to India and its culture. As a student at the École Normale Supérieure, he had established a relationship with Sylvain Lévy, the famous Parisian Indologist. He was taking Sanskrit classes, and he had nurtured in himself a firm intention of traveling to India someday. He writes in 17 that one day in 1929, Sid Ros Mahmoud, the vice-chancellor of Aligarh University, came to Paris and informed Lévy, with whom he was in contact, about a vacancy of a professorship of French civilization at that university. Weil tells us that Lévy phoned him and asked, "Are you serious about going to India?" Weil replied, "Of course." Lévy then inquired whether Weil would accept to teach there French civilization. Weil replied, "French or any other, I don't care. To go to India, I'd teach anything they want." Nice. Eventually, the position opening was delayed, but in the meantime, a chair of mathematics was declared vacant at the same university. Lévy and Weil immediately took advantage of the opportunity, and so it was that Weil set sail for India in early 1930, staying there for 2 years. Although Weil's relationship with the University of Aligarh was conflictual, the university was in need of a complete overhaul, and as it turned out, Massoud had invited Weil there precisely to put things in order. It is clear from what Weil writes in his apprenticeship that his stay in India was made for him one of the most interesting, perhaps the most interesting stay he'd made in his whole life. He writes, "Thus, in January 1930, began a stay that was to last more than 2 years, and which left me with a prodigious treasure trove of impressions. This plethora of stimuli can be compared only to what a small child takes during the first years of life on this earth, except that I was fully cognizant from the start. I still have vivid memories. In Sanskrit, the Brahmin is said to be twice born. Dvija, the second birth, is conferred upon him by the Brahmanic cord. It was not simply as a joke that, shortly before I was to return to France, my friend Vijaya Raghavan girded me with such a cord. Was it not the symbol of my second birth? Now to Simone Weil. While André is well known within the mathematical community as one of the most influential mathematicians of the 20th century, In the non-mathematical cultured community, the family name Weil evokes rather his sister Simone, 1909 to 1943, who is known as a socially committed intellectual, philosopher, and historical essayist, activist for workers' rights, and mystic. She was a thinker who aimed to bring together the foundations of ancient Greek religion, Hinduism, and Christianity, and the author of an oeuvre that attempted to do so. André and his sister shared the same ideas on several important issues. They admired and studied each other. They admired and understood each other from childhood, and they maintained a rich correspondence when life later separated them. They both possessed a formidable cultural background, including a profound historical vision and thorough knowledge of ancient science and languages. Above all, they shared a demanding and uncompromising attitude in their respective societies and milieu in which they lived, as well as an intransigent approach to the world of ideas in which they were evolving. Reading their respective biographies and the letters they exchanged in adulthood, it clearly appears that they had a fused relationship. Even when circumstances meant they ended up living in distant parts of the globe. In an interview with André concerning his relation with his sister, who was 2 years and 9 months younger than him, to the question, was there a strong intimacy between the two of you, he responds, a very big one. As a child, my sister would spend her time imitating me. My grandmother, who liked to speak German from time to time, said she was a Kopiermaschine. Also quoted in 22. It was probably because he was still so much affected by the very early death of his sister, age 34, that André does not directly refer to her as much as would have been natural, or at least he claims not to mention her enough. Claims not to mention her enough often. In his autobiography, written 48 years after her death, The Apprenticeship of a Mathematician, he writes in the foreword of that book, my sister, too, is not much mentioned in these memoirs. Some time ago, in any case, I recounted my memories of her to Simone Pétremont, who reflected them in her fine biography, Simone Weil, A Life. It would be superfluous to repeat herein those many details on our childhood, which are included in Pétremont's book. Classic mathematician, must be efficient. We have reduced it to a problem already solved. Go read her book. In spite of this, it's easy to guess while reading Apprenticeship that Simone Weil was always present in her brother's thoughts. She is also on most of this book's photographs. Let's quote another passage from Souvenir concerning his sister. As children, Simone and I were inseparable, but I was always the big brother and she the little sister. Later on, we saw each other only rarely, speaking to one another most often in a humorous vein. She was naturally bright and full of mirth, as those who knew her would have attested. She had retained her sense of humor, even when the world had added a layer of inexorable sadness. In truth, we had few serious conversations, but if the joys and sorrows of her adolescence were never known to me at all, if her behavior later on often struck me, and probably for good cause, as flying in the face of common sense, still we remained always close enough to one another so that nothing about her really came as a surprise to me, with the sole exception of her death. This I did not expect, for I confess that I had thought her indestructible. It was not until quite late that I came to understand that her life had unfolded according to its own laws, and thus also did it end. I was little more than a distant observer of her trajectory. Sylvie Weil, André's daughter, in the novel we discussed, describes how her father, in moments of absent-mindedness, would confuse her with his sister and call her Simone. Yeah. And that he sometimes unintentionally made his daughter feel like a reproach that she was far from the latter's intellectual level. She writes, genius was two-headed. My father had a double, a feminine double, a dead double, a ghostly double. For, yes, in addition to being a saint, my aunt was a double of my father, whom she resembled like a twin. A terrifying double for me, since I looked so much like her. I looked like my father's double. Sylvie also recounts that at times she was ashamed of her aunt, like the time she was at a dinner party and felt obliged to divert attention away from her aunt because a feeling of embarrassment toward the latter, so as not to answer a question from one of the guests asking if she was related to the philosopher, quote, who was admired by the Catholics and hated Jews. Oh my. All right, Section 3, Simone Weil, Christian Spirituality and Social Activism. Ads are going to start in a few minutes. Well, we're not going to get through it anyway for Section 3, but we can start that. Simone Weil grew up under the protection of her brother, who was brilliant in his studies. He passed his baccalaureate with honors at age 16, was ranked first at arXiv in mathematics at age 19, and was awarded a doctorate at age 22. Yow. During the First World War, their father was mobilized as a military doctor, and André did his schooling at home, studying alone from books. He taught his 5-year-old sister to read on the sly. The two children wanted to surprise their father. One day when he came home, Simone took his newspaper and started reading it. Let us move on to what Simone says about her relationship with her brother. We start with an excerpt from a letter written to Joseph-Marie Perrin, a Catholic priest who had become her spiritual mentor. The letter is dated 15th of May, 1942, and was later published as part of her spiritual autobiography, a collection of letters she wrote to Father Perrin between January and May 1942. The letter shows, first, a young Simone going through an existential crisis, stunned by her brother's achievements and finding herself excluded from the world of ideas, but who would later gain the innermost certainty that she would keep for the rest of her life, that any human being can attain truth if the intention and the effort to know are strong enough. She writes, at age 14, I fell into one of those bottomless despairs of adolescence and seriously thought about dying because of the mediocrity of my natural faculties. The extraordinary gifts of my brother, who had a childhood and youth comparable to Pascal's, forced me to be aware of this. I had no regrets about external successes, but about not being able to hope for any of the access that the transcendental realm where only truly great men can enter and where truth dwells. I would rather die than live without it. After months of inner darkness, I suddenly and forever had the most certainty that any human being, even if his natural faculties are almost nil, can enter that realm of truth reserved for genius, if only he desires the truth and makes a perpetual effort of attention to reach it. In this way, he too becomes a genius, even if for lack of talent, this genius is not visible from the outside. Later, when my headaches caused my few faculties to become paralyzed, a paralysis that I very quickly assumed was probably definitive, this same certainty made me persevere for 10 years in efforts for attention that had almost no hope of results. Sylvain Lévy was a French Indologist and professor at Collège de France, highest possible position in the French academia, 1863 to 1935. Syed Ros Mahmoud bin Mahmud Khan, 1889 to 1937, was the Vice-Chancellor of Aligarh Muslim University starting in 1929, that is, the year that André Weil started working there. At the latter's arrival at Aligarh, he stayed at Mahmoud's house for several weeks. Weil writes in his apprenticeship, at this time in India, it was beginning to be understood that an exclusively English view of the world was not suitable for India. Indeed, it was for precisely this reason that Mahmoud had brought me to Aligarh. Mahmoud was knighted by the British government in 1933. He was linked to the British novelist E.M. Forster, who dedicated to him his novel A Passage to India, 1924. All right, we're going to take our first ad break, so we'll be back in 3 minutes. See you all in just a little bit. Thank you so much for coming, and we'll be right back. Hello, welcome back. So the other books that we pulled out of that one box, one down. 3, 4, 5, 6 to go. Math Geek by Raphael Rosen. From Klein bottles to chaos theory, a guide to the nerdiest math facts, theorems, and equations. The Man Who Loved Only Numbers by Paul Hoffman, all about Erich. Game Theory by Morton Davis. I was going to cheekily give this to the president of our community college as a going away present for me, because she was attempting to anger the union on purpose. In fact, she angered the faculty so much that they created a union. Large print crossword. World's Most Perplexing Puzzles by Charles Barry Townsend. Critical Thinking Puzzles by Michael A. Despizio. Masquerade. Kit Williams. This book was originally one of the first big puzzle books that it was a bit strange of a thing. So 1976, Tom Maschler, chairman of publishers Jonathan Cape, came to see me. This, I think, is the author who's... I think it's the author. Yep, Kit Williams. He had seen my paintings at the Portal Gallery in London and wanted to know if I would illustrate a children's book. I explained I was a painter, not an illustrator, and anyway, I didn't want to draw pictures from someone else's story, so he suggested I write a story of my own. I'd never written anything in my life, so I said no to that too. He left saying, I bet you could do something with books that no one has ever done before. Some weeks later, an idea came to me while I was eating breakfast, but I told it to go away. I was much too busy to be bothered for ideas about books, and started thinking about what books are and how they work. By dinner time, the first idea was back with a friend, and soon a whole room was full of ideas. I couldn't resist the thought of a book that a lot of people would want to examine closely. I rang up Tom Maschler for an idea and said I needed £3,000. He didn't seem to understand completely how it would work, but very bravely sent me a contract straight away. What I wanted to do was retain the format of a book, but then do something different with it. If I was going to spend 2 or 3 years doing 16 paintings, I didn't want them to just be flicked through and put down. And that's why the perspective is odd in some of the Masquerade pictures, why some others overlap with their borders. Some things come straight out at you, all to make you look really closely. The riddles and treasure are also partly to make people look. Little did I know how hard they were going to look. So he did this treasure hunt because back in the day he had competitions that were on cereal packets that were pretend treasure hunts. And so he was like, nah, I want to do the real thing. So he eventually figured out how to do it and came up with a prize that was like a silver rabbit with like flowers and stuff all through it and things coming off, which was hidden inside a fake stone, turned over and sort of semi-buried somewhere. So I thought I would go through that eventually at some point. Haven't yet, but you know, math jokes for mathy folks with such corkers as sales lady, this vacuum cleaner will cut your work in half. Great, I'll take 2 of them. Yeah, math puzzles. This one's got a bunch of Sudoku, a bunch of the Kakuro puzzles, and then logic stuff, and all sorts of other fun things. Solve It, A Perplexing Profusion of Puzzles by James Fix. A Strange Series. The following number is the only one of its kind. Can you figure out what is so special about it? 8,549,176,320. Figured out some of it. And Mathemagic. Classic Mathemagic. Raymond Bloom, Adam Hart Davis, Bob Longa, and Derek Needleman. Same sorts of things. Which 2-digit number is 1 more than a square and 1 less than a cube? Got it. First guess, too. It was... I did actually guess. Yeah, those are answers. Can you replace the missing digits in the number 789,000XYZ so that the resulting number is divisible by 7, 8, and 9? The only restriction is that you cannot use a 7, 8, or 9. Hope y'all are having a good evening. So we'll fit all the physics books back in here. Oh dear. Alright, good enough for now. It's a little warm in here, unfortunately. I can't open the door because the kids' rooms are just across from me, and I can't open the window because there are moths outside. And Britain is notorious for not having screens over their windows. So all manner of stuff comes in when it's not like super windy. Which, to be fair, it usually is super windy here. So I'd be able to open the window, but not today. All right, back to it. So, let's see. Okay. Next footnote. Tirakana Puram Vijaya Raghavan was a young mathematician, 1902-1955, who had studied with G.H. Hardy at Oxford in the mid-20s and who was recruited at Aligarh University by Weils after his arrival there. In 1930. As a matter of fact, his apprenticeship, Weils mentions the names of 3 young mathematicians he met during his stay in India. I had some regrets that my efforts had failed, but at least they had succeeded in creating bonds of friendship among Vijaya Raghavan, Kosambi, and Chawla, the 3 young mathematicians who seemed to me the most promising at the time. Yeah, copy machine. Yeah, copy machine. Got that. Baccalaureate is the French National High School diploma. André Weils passed 2 baccalaureates, sciences and humanities, which he took in succession. He got the mention très bien, which is the highest rating for both. Very well mentioned. The French agrégation is a very selective French diploma entitling the holder to teach in a high school with substantial salary, fewer class hours, and other privileges. Most French mathematicians had started by passing the agrégation. Once one has successfully passed this competitive examination, unless one continues for a PhD, he or she is appointed to a specific town, depending on ranking, and also on the current need for teachers. Weils obtained his agrégation in 1925 at age 19, which is very exceptional. In her letters to J. M. Perrin, Simone Weils makes explicit her attachment to the Catholic Church, but her refusal to get baptized, not least because her allegiance and faithfulness to other spiritual traditions, especially those of ancient Greek philosophers and Hinduism, an allegiance for which the official Catholic Church would condemn her for heresy. She also writes in the same letter to Friar Perrin, the pure and simple resolution not to think about the question of my possible entry into the Church is quite possible. It is quite possible that one day I will suddenly feel the irresistible impulse to ask for baptism at once, and I will run to ask for it. Okay. Simone entered École Normale Supérieure at age 19. Her brother had entered at age 16. Not in mathematics as her brother, but in the humanities section. At the École, she, together with some of her fellow students, took part in political actions, primarily through petitions, gathering money for a union strike fund or for unemployment funds, collecting signatures for an appeal against military preparation that granted officer rank through shorter military service, and she was involved in many other causes. These activities are recounted in detail. In September 1930, after obtaining agrégation, Simone Weils was appointed philosophy professor at high school in Puy-en-Velay, a provincial town in central south of France. There, in those difficult pre-war years, she very soon became active in the trade union movement, supporting workers' strikes against unemployment and falling salaries. Shortly after her starting her work as a teacher, she decided to live on the minimum wage paid to the unemployed in the town where she was teaching, donating the remainder of her salary to workers in need. She became a union activist, contributing essays in syndicalist and revolutionary journals, and she joined anarchist and communist circles, publishing articles in the Marxist periodicals La Critique Sociale, La Révolution Prolétarienne, and other left-wing publications. She was following, with much anxiety, Hitler's rise to power in Germany at the same time, while also being critical of Stalin's repression policies in the Soviet Union. while also being critical of, just read that. She once had a stormy discussion with Leo Trotsky in her parents' apartment where she had invited him. Trotsky was at that time Stalin's most famous opponent. He was living in exile and passing some time in Paris. With his wife, child, and bodyguards, he stayed in Simone Weil's parents' apartment at her invitation. Even if she was attracted by Trotsky's ideals, Simone Weil was more critical than he was concerning the effects of the October 1917 revolution, especially with regard to the one-party regime and the bureaucracy that had taken hold in Russia and was crushing the working class. The discussion between Simone Weil and Trotsky is reported on several writings of her and about her, in particular the booklet Conversation with Trotsky. See also her comments in the following books, articles, and article by Trotsky. This encounter was also mentioned in 7 and 17. At some point in Le Puy-en-Velay, Simone Weil joined a group of unemployed workers at a town council meeting and spoke on their behalf. For this, and more generally for her publicly expressed strong political views, the school where she was teaching asked for her replacement. At that time, André Weil, who was working in India teaching at Aligarh University, relates the following episode in Apprenticeship. Jean-Paul Sartre and Simone de Beauvoir, who were of Simone Weil's generation and who, like her, passed the philosophy agrégation, both obtained it in 1929, ages 24 and 21 respectively. Sartre was ranked first, Beauvoir second at the national exam. In fact, this was the second year Sartre had taken his exam, first time he failed. André says, while I was in India, my mother had kept me up to date on the eventful life my sister, the trolless, or female troll as we called her within the family, in Le Puy, where she had obtained her first appointment as a philosophy professor in a girls' lycée, high school. Because Simone had been so bold as to shake hands with unemployed workers in a public square and then to accompany their delegation to the town council, the school administration had threatened her with disciplinary action. This news had reached me just when I was fighting my own battles with the administration at Aligarh, and naturally I was enchanted with the way my sister stood up to the authorities. I had written her a letter of congratulations, saluting her as amazing phenomenon, to which she replied, addressing me philosophically as noumenal. It is reported that the discussion was stormy and it focused on a particular role of the German Communist Party in triggering the revolution. Trotsky, who was surprised by Simone Weil's attitude, asked her, "If you feel this way, why are you receiving us? Are you the Salvation Army?" It is also said that Natalia Sadova, Trotsky's wife, stunned by this discussion, exclaimed, "Look at this child standing up to Trotsky." The whole group finished the evening in a local movie theater where the film Ukraina by Soviet director Boris Barnet was being shown, a film based on Konstantin Finn's eponymous novel. In 17, Weil writes concerning 13. The encounter. Yeah. Weil writes, my sister, pursuing her eventful career, had begun to receive her German friends fairly often at her parents' home. Our parents were sometimes troubled by these lengthy visits. Most of these Germans were dissident socialists or communists who had fled from Hitler. Unbeknownst to me at the time, even Trotsky stayed at my studio once at the end of 1933. In the Kantian philosophical language, critique of pure reason, the term noumenal designates an object of pure thought, which exists independently of our sensory perception, as opposed to the phenomenon, which is the object of our sensible experience. The two Weils used to play with words such as these to address each other. So he writes to her, saluting her as amazing phenomenon, as in somebody who is well within the perception of everybody around them, whereas she calls André noumenal, meaning somebody who is outside of perception, somebody who is keeping their head down, I guess. Indeed, the letter written by André Weils to his sister, dated 5th November 1931, starts with, "Amazing phenomenon, I heard about your achievements and cannot resist sending you my warmest congratulations." In another letter, dated 14th January 1932, also sent from Aligarh, André calls his sister champignon sur l'humeau, or fungus on top of hummus, in reference to an article in a conservative regional newspaper that claimed that intellectuals who want to make it grow in the misery of the poor like mushrooms on hummus. Oh, humus, sorry. So close. It has been, I think, 23 years since you entered the phenomenal world, much to the annoyance of rectors and headmistresses, but I wouldn't take up my pen on such trivial occasion if I didn't have more worthy reasons to send you my warmest congratulations and encouragement to persevere in a path you've opened up for yourself. As for my hoaxes, which are so abundant, my letters from Paris will give you all the details you need. The University of Aligarh is in disarray, it is a mess, and I can at least flatter myself that I gave the signal for the debacle. I am strongly considering returning via China and Russia, and am working on Russian grammar. He concludes the letter by the words, Inkilab Zindabad, which in Hindustani means "long live the revolution," uttered during India freedom struggle in the 1920s. Okay. Simone replied in a letter written at the end of January 1932, "I will never forgive you if you see the USSR before I do." In the same letter she writes, "You're a disruptive element too in your own way, as I see. You gently demolish the universities that you pass through. Here, miners strike in preparation. The situation is pathetic. Depressed proletariat, increasingly violent polemics between union tendencies." Like her brother, she ends the letter with Inkilab Zinabad, with a drawing of the sickle and hammer above her signature. The letter is written on a miners' union letterhead paper. Yeah. I mean, intentions, very clear. In 1934, Simone Weil resigned from her teaching position in the intention of working as a factory worker. The reason was that she wanted to physically feel the great fatigue of assembly line work and the oppression, social suffering, and anguish of unemployment experienced by the workers. She first worked at the Alstom factory in Paris, a factory which in those times was a mechanical construction plant. After Alstom, she worked as a laborer in the steel industry at the forges of Basse-Indre on the outskirts of Paris, and later as a machinist at Renault, as in the car company, I believe. Each of the factories where she worked, she asked to be assigned to the most strenuous jobs. She wrote to a friend that she had been dreaming of doing this kind of work for 10 years. Let us quote her from a letter she sent to Boris Souvarine in 1935, in which she describes her working conditions. "Dear Boris, I am forcing myself to write you a few lines because otherwise I wouldn't have the courage to leave a written record of my first impressions of my new experience. The so-called friendly little company turned out to be on contact, first a rather large company, and then, above all, a dirty, dirty company. In this dirty company there is a particularly disgusting workshop. It's mine." Needless to say, Simone's parents, who lived a comfortable life in Paris, her father was a doctor, were very worried about her. All this is recounted in detail in the biography written by Pétremont and in other biographies, but most of all in her diary, notes, and correspondence published in her collected works. In addition, for several consecutive summers, she worked in farms, harvesting grapes, potatoes, and other earth produce at a frenetic pace, always wanting to do more. She also worked with fishermen at sea. From a certain point on, she was immersed in Christian religious texts. Later, she would write to her father Perrin, "Peasants and workers possess that incomparably sweet closeness to God which lies at the bottom of poverty, lack of social consideration, and long, slow suffering." Meanwhile, the Spanish Civil War had broken out, a war between the so-called Republicans, comprising the left, the far left, and the anarchists, and the nationalists, comprising the right-wing parties, the fascists, also known as the Francoists. Simone Weil went to Spain to join the anarchists with the objective of fighting the fascists, after having persuaded her parents that she was going to Spain as a journalist. She was only able to stay for a few months and was repatriated to France after a domestic accident in which her foot was badly burned. Oh dear. André Weil had a number of conflicts and setbacks with the administration of the University of Algar, which led to his ousting, but this is another story. Boris Souvarine, 1895 to 1984, was a political activist, journalist, historian, and essayist, and a friend of Simone Weil. His real name was Boris Lifshitz. He chose a pseudonym, Souvarine, after the character in Émile Zola, a Russian immigrant and anarchist working in a coal mine in northern France. Souvarine was initially a communist activist before being excluded from the PCF in 1924 after he criticized the leadership of the Communist Party in Russia. An outspoken critic of Stalinism, Souvarine is the author of an early biography of Stalin. It seems that the accident happened in a kitchen where Simone had been assigned. In fact, in her stay in Spain, she was refused assignments at the front because she was extremely clumsy and totally impractical. Oh dear. Everyone knew she was not able to handle a rifle. The same thing happened again when she was asked to be sent to the front in France to fight with the resistance against the Germans in Vichy regime. Her request was refused. Well then. Greek, Sanskrit, and Bhagavad Gita. Simone Weil was deeply attached to the cultures of ancient Greece and of India. Readers will have gathered that it was her brother who first exhibited this attachment. We've already mentioned that during the First World War, André Weil did most of his schooling at home. We learned from his apprenticeship that by 1917, he was 11, he knew enough ancient Greek and mathematics which he learned on his own. He writes, "When school reopened in October of 1917, my family was in Laval. I taught myself enough Greek, and I already knew enough mathematics, to be admitted into classical section of the third form, which is the fourth last year before finishing high school." Fourth comma last year before finishing high school, I think. I no longer remember whether it was there that I read my first book of the Iliad, or whether I read it by myself for my own pleasure. In any case, that was how I discovered poetry, and that it is untranslatable, pretty much. Later, his sister also became a fervent devotee of ancient Greek literature. Readings, notes, translations from ancient Greek, and fragments of studies on ancient Greek thought that she wrote Ancient Greek thought that she wrote were published in 1953 in a volume titled La Source Grecque, the Greek source. We shall talk about Sanskrit. It was during the same period that André Weil learned ancient Greek that he became interested in Sanskrit. We read on page 24 of The Apprenticeship, "I had at the time, and indeed I still have, Anna Dale's English Dictionary, which includes an introduction to Indo-European linguistics and Grimm's Law, as well as fairly detailed etymological information going as far back as Sanskrit. I dreamed of one day being able to read, in the original, the epic poems written in all these languages." Mood. My romantic notion of these epics later led me to seek out Sylvain Lévy's advice. Fortunately, too, my courses began at the classe préparatoire did not fill all of my time that year. I began to study Jordan. As in Jordanian? Oh no, Camille Jordan. Okay. I began to study Jordan. Also, my precocious and romantic attraction to Sanskrit gave one of my father's friends the idea of introducing me to the leading scholar in the field of Indian studies, Sylvain Lévy. When Lévy received me at his home in Rue Guy de la Brosse, he said to me, "There are 3 reasons for studying Sanskrit," and he enumerated them. I believe they were Veda, grammar, and Buddhism. Which of these is yours? I didn't dare tell him that I was impelled by none of these 3, but rather this simply by the naive notion that I had of Indian epic poetry. I had already learned, where I do not recall, the alphabet had 1 or 2 declensions, and I asked his advice on how to proceed. He told me that the best textbook by far was Bergagne's, but it was out of print. Otherwise I should obtain a copy of Victor Henry's textbook. This I bought immediately, and I lost no time putting it to use. Charles Annandale. Charles Annandale, Scottish editor, 1843-1915, especially of reference books. ArXiv refers probably to concise imperial dictionary, literary, scientific, and technical, with pronouncing lists of proper names, foreign words and phrases, key to names in mythology and fiction, and other valuable appendices, published around 1950. Grimm's law describes a series of phonetic transformations that trace the evolution of the occlusive consonants of Proto-Germanic, the ancestor of today's Germanic languages, from those of Common Indo-European during the first millennium BCE. Seeking out Sylvain Lévy's advice, see footnote 3. 23. Classe préparatoire. In the French system, these are 2 years of study that follow baccalaureate and prepare students for the entrance examinations to the Grande École, that is, universities, that have the rank superior schools, which, in the case of André and his sister, is the École Normale Supérieure. And incidentally, André V entered the École Normale after 1 year of classe préparatoire instead of 2, which is extremely rare. Jordan is the mathematician Camille Jordan, 1838 to 1922. In his apprenticeship, V recounts that Lycée Saint-Louis, the year he was preparing baccalaureate, awarded an endowment prize to the best student in mathematics. The prize went to him, and he received as a reward the 3-volume Cours d'Analyse by Jordan and the Treatise of Natural Philosophy by William Thomson, later Lord Kelvin, and Peter Guthrie Tate. He writes then, thanks to Adamar, I learned analysis from Jordan, infinitely better than learning it from Goursat, as most of my classmates did, and I was initiated into differential geometry by Thomson and Tate. Naturally, I did not read those hefty volumes immediately. I think, however, that I did begin with Jordan the following year. In 1922, André V is a student at École Normale Supérieure in Paris. He writes in the apprenticeship, at the end of the year, wishing to devote part of my vacation to reading a Sanskrit text, I went to Sylvain Lévy for advice. From a shelf in his library, he pulled a small volume bound in red velvet. It was a native, to use the term in vogue at the time, edition of Bhagavad Gita. Read this, he told me. First of all, you cannot understand anything about India if you haven't read it. Here he paused, and his face lit up. And besides, it's beautiful. With the help of a dictionary lent to me by Jules Bloch, and of the English translation of Sacred Books of the East, borrowed from the École Library, I read Gita from cover to cover. The beauty of the poem affected me instantly, from the very first line. As for the thought that inspired it, I felt I found in it the only form of religious thought that could satisfy my mind. My sister and I had been brought up without any semblance of religious education or religious observance. Later on, I felt at home in India thanks to the Gita, and much later, it was also thanks to the Gita that my sister's way of thought did not seem at all foreign to me. During his second year at École Normale, Weils regularly attended Jules Bloch's course on the Veda at the École des Hautes Études, Meillet's lectures on Indo-European linguistics, and Sylvain Lévy's on Karidesa's Meghaduta. I don't know that one. Talking about the latter, Weils recalls, in Millet, already nearly blind, this was said to be from deciphering numerous indecipherable texts from Central Asia, would hold forth extemporaneously, treating his audience to observations which even my ignorant mind could tell were strikingly original. Sylvain Lévy read and explained the Kalidasa poem verse by verse in his slightly muffled voice. About 50 years later, and at the time he was composing the apprenticeship, Weils writes, and I continue with as much enjoyment as ever my reading of the Gita. I often had reread certain passages, but I had read it straight through from beginning to end only once in 1923 or 24, and I am pleased with myself for remembering my Sanskrit well enough to read such a text. André Weils and his Dharma. In this section we shall be talking about Dharma, the complex and multivalent word in Indian religions and spirituality. The few words that follow are aimed primarily at the Western reader unfamiliar with Indian culture. I did take a course on history of world religions, but that was a long time ago, and also, we didn't study that much in depth. The word dharma can designate a set of norms, which may be social, family, or personal, or a natural and cosmic law, which may be universal. It can also simply refer to a personal truth or reality. It also means one's social or moral responsibilities or duties. We quote, and shall quote again in this context, the sentence by André Weils, Gauguin's Dharma was painting. Mine, as I saw it in 1938, seemed clear to me. It was to devote myself to mathematics as much as I was able. In any case, it is probably in the various uses of this term by André et Simone Weils, in the lines that follow, that its meaning in the present context will become clearer. In the apprenticeship, André Weils shares his thoughts on compulsory military service, especially in times of war. He tells us that in his first years at École Normale, he was already struck by the fact that in France during the First World War, an entire generation of researchers were sacrificed, since even those who returned after 4 years of war were no longer capable of exercising any scientific research profession. He writes, "This was a fate that I thought it my duty, or rather my dharma, to avoid. I was not a conscientious objector in the sense of usually given to this word, that is, someone who does not believe in killing or even using instruments of death, whether he sees this as a universally valid precept or as his own personal dharma. He makes it clear that this was not a question of pacifism, and that he feels himself to be as much far from an unconditional pacifist as from uncompromising patriots. He tells us that this course of action in 1940 got him into a series of troubles, which he says caused his sister a crisis of remorse, as she considered that, because at some point she had pacifistic inclinations, she might have influenced him in his decision not to submit to the regulation of national service for all. He says that if there was one thing that influenced him, it was the example of the mathematician Carl Ludwig Siegel, who told him how he had once deserted in 1918 while serving as a soldier in the German army in Alsace. It seems that Siegel had told him, Das Krieg war nicht mein Krieg, which means, this war is not my war. This passage on the war ends with the words, In this light, I felt justified in thinking that by exempting myself from military law, I was, to the small extent permitted me by my circumstances, taking charge of my own destiny. At the moment he was called up as a soldier, it was the Gita that helped André Weils make a decision. In the apprenticeship, he writes, I have been deeply marked by Indian thought and spirit of the Gita, such as I felt capable of interpreting it. He's referring here to the passage of the Gita known to the Hindus, in which Arjuna, the very famed warrior, crippled with emotions, expresses to Krishna doubts whether or not to go into battle because he does not understand the reason why he has to go and fight and kill people from the other clan, who are also members of his family. This was during the Mahabharata war, which pitted Kauravas against the Pandavas, two groups from the same family. Krishna's response to Arjuna can be summed up by the fact that the latter is a warrior and that his duty is to fight. The question thus, indeed, concerns the faithfulness to one's dharma. About his own dharma, André Weils writes in The Apprenticeship, after again quoting the Gita, that the only recourse is for each one of us to determine as best he can his own dharma, which is his alone. Gauguin's dharma was painting. Mine, as I saw it in 1938, seemed clear to me. It was to devote myself to mathematics, as much as I was able. The sin would have been to let myself be diverted from it. Weils' refusal to serve in the army was not properly interpreted by some of his colleagues. Cartier will later write, some translated this crudely as, my brain's too precious to be exposed to bullets. Or, to go to war would waste my invaluable time while I am full of exciting discoveries. This was seen as nothing more than egotistical translation, in a time of crisis, of the pure mathematician's motto, which is quite common in our milieu, and which often serves as an alibi for shirking responsibility. This had consequences on Weils' career, which we shall address later in the article. In any case, later in the article. Don't have that much left to go. Because he refused to join the army, Weils spent 5 months in prison in Rouen, a city in Normandy. We might add in passing that he would later say that, from a mathematical point of view, these 5 months constituted one of the most productive periods of his life. Sanskrit and the Gita accompanied him during the period of his incarceration. Let us quote a few passages from the letters he sent to his wife Aveline from prison. These excerpts are produced in 17 from a letter sent 30th of March 1940. And then there are always my Sanskrit books. I am reading the Gita in small doses, as one ought to read this book. The more detail one absorbs, the more one admires it. On 7th of April, same year, he writes, here are some lines from the Gita that I like very much. A leaf, a flower, a fruit, some water. Whoever dedicates it with love, this love offering I accept with devotion of his soul. The god Krishna is speaking. In Tamil, it is written of him, the bread we eat, the water we drink, the betel nut we chew, this is our Krishna. It is almost impossible to translate all of this. In everything to do with gods, our language is slanted toward the idea of a personal god that is totally foreign to the Indians. The question would come up later again when André had left France. His sister, who was part of the France Combattante, in a letter sent on 23rd of April 1943, asked him to join the organization, specifying that membership implies only the affirmation that it was right and proper in June 1940 to proclaim France's continued participation in the war, something I have never doubted. Weils refused. André refused. He replied that by joining the FC, one necessarily places oneself at the disposal of the military authority, something I am loath to do, and which would only be excusable in my own eyes if I had decided to become a military man in the strict sense of the word. Again, it was a question of dharma, and André Weils quoted the Gita, either you completely become a soldier or you remain, as you are now, a Brahmin, and in the latter case you devote your life to intellectual activities, teaching, learning, and meditation. You cannot be both at the same time. As he writes in The Apprenticeship, it seems fitting for me to indicate here the motives behind my resolution not to serve. Though I fear this may turn into a long and confused explanation, I thought I was being perfectly lucid at the time, but is one ever perfectly lucid when making a decision of grave impact? I have never believed in the categorical imperative. The Kantian ethic, or what passes for it today, has always seemed to me to be the height of arrogance and folly. Claiming always to behave according to the precepts of universal maxims is either totally inept or totally hypocritical. One can always find a maxim to justify whatever behavior one chooses. I could not count the times, for example, when I tell people I never vote in elections, that I have heard the objection, "But if everyone were to behave like you," to which I usually replied that this possibility seems to me so implausible that I do not feel obligated to take it into account. On the other hand, I have been deeply marked by the Indian thought and by the spirit of the Gita, such as I felt capable of interpreting it. The law is not, "Thou shalt not kill," a precept which Judaism and Christianity have inscribed, but to what avail, in their commandments. The Gita begins with Arjuna, filled with deepest compassion, stopping his chariot between two armies, and ends with his lucid acceptance of Krishna's injunction to go into combat unflinchingly. Like everything else in the world, combat is an illusion. He does not kill, nor is he killed, whoever has known the self. In the absence of any universal recipe to prescribe everyone's behavior, the individual carries with him his own dharma. In the ideal society of mythical times of Mahabharata, the dharma comes from the individual's caste. Arjuna belongs to the caste of warriors, so his dharma is to go to combat. Krishna is the exceptional being, the divinity incarnate. Whatever dharma declines and its opposite triumphs, I reincarnate myself, he says in a famous verse, which was once applied to Gandhi. Krishna exists outside the Dharma. The question for André Weils, if he solved it for himself, wasn't as easy as that. Indeed, he had advised his sister, who was a fighter for social justice, to leave France too. Calicon! Good evening. Yep, he was in jail for 5 months, and I believe that this is the same jail that ended up getting shelled like a couple of days after he was either released or taken to a different prison. I can't remember what it was, but I think the prison that he was at was shelled like within days of him leaving. She would leave France too, which she did in 1942, but something she would later regret. She wrote him from England in a letter sent from 17th of April 1943. He was in the USA. "I am torn more and more cruelly day after day by regret and remorse for having been weak enough to have followed your advice a year ago." Jeez. And she adds, "As for you, if you were now in conditions favorable to mathematical work, I would certainly advise you to think only of mathematics, and that definitively, if possible, until death." Meanwhile, André was being criticized in France by certain colleagues for deserting. Cartier writes in number 7 that Weils would like to have settled in France, but was prevented from doing so. The Patriot Party, he writes, never gave up on him. The most relentless member of the Patriot Party was Jean Leray. Leray worked hard to keep Weils out of the Sorbonne and the Collège de France. Weils stayed in Chicago, and my generation lost a master. To conclude this section, we quote an excerpt from Antoine de Saint-Exupéry's Terre des Hommes, in which the author speaks about truth. Terre des Hommes. The title of the English translation is Wind, Sand, and Stars, which is not a translation. It gets the vibe, but you know. Terre des Hommes is Earth of Men, or Earth of Man. And Wind, Sand, and Stars is, yeah, definitely not that. Jean Leray also had a crazy backstory. No, I did not hear that. The ideas about this passage are very close in substance to what André writes about his Dharma. Truth is not not that which can be demonstrated by the aid of logic. If orange trees are hardy and rich in fruit in this bit of soil and not in that bit of soil, then this bit of soil is what truth is for orange trees. If a particular religion or culture or scale of values, if one form of activity rather than another brings self-fulfillment to a man, releases the prince asleep within him unknown to himself, then that scale of values, that culture, that form of activity constitute his truth. Logic, you say? Let logic wangle its own explanation of life. In guise of a conclusion. Throughout her life, Simone Weil, like her brother, refused to make concessions. J.M. Perrin writes that we cannot fully understand her if we forget the sharp character that emerged from her thirst for the absolute. He quotes her saying that the greatest evil is not evil, but a mixture of good and evil. To the same, Simone Weil writes in the letter dated 15th May 1942, in the spring of 1940 I read the Gita. Strangely enough, it was while reading these marvelous words, so Christian-sounding, put into the mouth of an incarnation of God, that I felt strongly that we owe religious truth something more than adherence to a beautiful poem, a kind of adherence that is much more categorical. 9th of June 1943, that is a month and a half before her death, in a letter to her parents sent from London, where she had been exiled against her will, Simone writes, I started doing a few lines of Sanskrit every day in the Gita. It feels so good to be in contact with Krishna's language. At the end of the same letter, she tells her mother, enjoy the beautiful days and think of Krishna. Until the last moment, she was hiding the fact that she was ill with an extreme form of anorexia. She passed away in a sanatorium in Ashford, England, 24th of August, 1943, aged 34. She had contracted tuberculosis, but what had led her to death was physical and moral exhaustion and starvation. She could not accept to get nourished normally while her compatriots were starving under Nazi occupation. Almost all of her works were published posthumously. From 1949 onwards, Albert Camus was responsible for publishing some of her most important writings. In a letter to her parents, he wrote that their daughter is the only great spirit of our times. The complete works of Simone Weil are published in 7 tomes distributed over 16 large volumes. After Chicago, André Weil joined Princeton's Institute for Advanced Study. Now, IAS is a big one, where one of his colleagues, J. Robert Oppenheimer, also known as a lover of Bhagavad Gita, also read Sanskrit. We know the famous verse, I am now become death, the destroyer of worlds, and the fatal moment of the test of the known as Trinity test, 16th July 1945, when Oppenheimer recited it, but that is a separate subject. Let us conclude by quoting André from his memories of his prison in Rouen. The door, like that of a safe, but pierced with the usual peak hole, opened with a loud rattling of keys and grinding of hinges, aptly illustrating the expression as graceful as a prison gate. I had with me the Bhagavad Gita, the Chandogya Upanishad, novels by Balzac, and, on my sister's enthusiastic recommendation, Retz's memoirs. I also had what I needed to resume my mathematical work. I often recited to myself the lines of the Gita, Patram, Puspam, Pharam, Toyam, a leaf, a flower, a fruit, water. For pure of heart, everything can be an offering. First author gratefully acknowledges invitations to several institutions in India where this paper was written. Banaras Hindu University, Jawaharlal Nehru University in Delhi, Tata Institute for Fundamental Research in Bombay, International Center for Theoretical Sciences in Bangalore. Discussions with Subhabrata Das were especially enlightening. I'd like to thank Arkady Plotnitsky, Alexei Sosinsky, and Bharath Sriraman, who took trouble to read carefully a preliminary version of this text, give impressions, and ask for clarifications. We also thank Himalaya Senapati for his help with Sanskrit. J. Robert Oppenheimer was the a professor at IAS for a period of 1947 to 1967, served as director for the Institute 1947 to 1966, and thus far the longest tenure of any Institute director, and it was at a time when André Weils was a member. Cardinal de Retz, Jean-François Paul de Gondi, 1613 to 1679, is a French ecclesiastic known as a writer for his Mémoires, an invaluable document for historical and sociological information it contains. Cool. All right. Thus endeth that one. So we've got another ad break that's popping up just like now. We'll see you all in 3 minutes. Be right back. Cartier passed away a year ago. I would have imagined it was earlier, but yeah, he was the generation after, so makes sense. He was a guy who was an expert in partial differential equations, but also had algebraic topology. So when he got captured by the German, he lied about doing PDEs, probably not be used for ballistic computations. So during his time being captured, he worked on algebraic topology, came out with the notion of sheaf. Turns out to be a very fertile idea that influenced many branches of mathematics in the second half of the 20th century. I mean, that's pretty awesome. All right. Last. $33 pages. Yeah, we're not getting through this whole thing, but stability analysis of time periodic solutions to the Navier-Stokes-Fourier system in 3D whole space by Naoto Deguchi. Paper concerns large time behavior of perturbations around time periodic solution to Navier-Stokes-Fourier system in the three-dimensional whole space. The time periodic solution exists when a given external force is small enough. We derive the time decay estimate of perturbation under the assumption that an initial perturbation is sufficiently small. Time-space integral estimate for the linearized semigroup around the constant state in the Bezov spaces is effectively applied in the proof. No idea. But it's all good. Oh, you liar. You did not finish all of these. Most certainly did not do every single one of the things in my playlist. All right. 1. Introduction. The motion of a compressible, viscous, and heat-conducting fluid is described by the Navier-Stokes-Fourier system for the density ρ, the velocity v equaling vector v1, v2, v3, and temperature theta. Partial derivative with respect to t of ρ, that's the density, plus the divergence. There we go. Divergence of the product of ρ and v is equal to 0 in r by r3. So that is time through 3 space. All right, the partial with respect to t of v, the velocity, plus the velocity dotted with the, come on, nabla. You know what this is. It's when the steep, the steep direction. Oh, what the hell? Am I getting back into the field of PDE research? No, I was never in it. As can be pretty obviously shown right here. I don't know what the F I'm doing. Yay! God. Fastest way down a hill. Come on. I've been doing this for how many years? I'm gonna hit myself. As long as I have fun, that's what matters. I mean. Oh, shush. No, I don't want a cycloid. You jerks. Gonna hit myself. Alright, let's go to Paul's. Gradient. Damn it. The gradient of V dotted with, or back dotted with V, plus the derivative with respect to T of V is equal to mu over rho. Doesn't even tell what mu is. That's awesome. Times delta V plus mu prime over rho times the gradient of the divergence of V minus the gradient of P over rho plus F. Oh, there you go. Mu and mu prime are viscous coefficients. Yeah, thank you. Yeah, it's right in the next paragraph. And then the partial derivative of T with respect to T of theta, which is again the temperature, plus V dotted with the gradient of theta, plus theta times the partial derivative with respect to theta of P, again the pressure function, divided by C sub V, specific heat at a constant volume, times rho, the density, times the divergence of V is equal to kappa, the heat conductivity coefficient, over C sub V times rho, times delta theta, plus capital Psi, which is the dissipation function given by the thing below it, which is really big, and I'm not reading that out loud, over C sub V times rho. Yikes. Oh. Okay. Throughout this paper, we assume coefficients mu prime, kappa, and C sub V are constants. Good. We satisfy kappa and C sub V are positive, and the thermodynamic restrictions, mu is positive, and also 2/3 of mu plus mu prime is greater than or equal to 0. I'm guessing that that has something to do with the eigenvalue. It has to be like a particular set of numbers. The pressure P is assumed to be a smooth function of rho and theta, satisfying the stability conditions. Partial derivative of density with respect to pressure is greater than 0, and partial derivative with respect to temperature of pressure is also greater than 0. let F be time periodic force with time period t greater than 0. Okay, that wasn't 3 space. This is our R3 here is what is it? V, yeah, rho v theta, with respect to time being our first R here. Okay, flow generated by F is described by the solution to the following time periodic problem. That big thing. In this paper, we consider time periodic problem 2 around the constant state, rho infinity 0, theta infinity, with rho infinity and theta infinity being greater than 0. Now, if I'm right here, theta infinity and rho infinity are like asymptotic to a particular value. Time periodic problem has been extensively studied for incompressible Navier-Stokes equation. Here we refer to Miramonte, Cozono Nakao, Yamazaki, Galdi Silvestre, Kobayashi, Kutsera, and many others. In particular, Yamazaki derived the time decay estimates for perturbations around a uniformly bounded in time solution, including time periodic solution to incompressible Navier-Stokes equation in unbounded domains such as whole space, half space, or exterior domains of dimension n greater than or equal to 3, under the assumption of smallness for both external force and initial perturbation. For the isentropic compressible Navier-Stokes equation, the existence and stability of the time periodic solution were studied by Vali in a 3D bounded domain and by Kagai Tsuda and Tsuda in Rn n-dimensional space n greater than or equal to 3. For the non-isentropic case, Ma, Ukai, and Yang proved the existence and stability result for the compressible Navier-Stokes system in n space where n is greater than or equal to 5, and Tsuda proved the existence and stability result for compressible Navier-Stokes-Korteweg system in R3. We also mention Weils show the existence of at least 1 week time periodic solution to Navier-Stokes-Fourier system in 3D bounded domain for large data. The time decay estimate for perturbation around a time periodic solution was derived by Ma, Ukai, and Yang for the Navier-Stokes-Fourier system under smallness assumptions. They proved decay estimate. Magnitude of rho minus rho t, the time periodic solution, v minus vt, and theta minus theta t of t. So the current value is distance to the time periodic solution value, whatever it ends up being. In subscript hn minus 1, which is the inhomogeneous Sobolev space defined in the end of the section. All right, so okay, so rho v theta is not the current value, it's the global solution with n being greater than or equal to 5. Must be less than or approximately equal to 1 plus t raised to the negative n over 4 times the magnitude between the differences of the initial pressure, velocity, and temperature compared to its time periodic solution at 0. L1. I don't see an L. No, that's just me. Probably. There's no capital L. So the fact that it's L1 intersected with the inhomogeneous Sobolev space defined at the end of the section, it's not really going to help me anyway, but the decay rate in the above corresponds to that of the heat semigroup. However, proof of decay estimate in 11 relies on the dimensional assumption that n must be greater than or equal to 5. In this paper, we aim to establish the decay estimates for perturbations around the time periodic solution to the Navier-Stokes-Fourier system in the physically important three-dimensional case. Let us state our main theorem, which derives the decay estimate for perturbation. T being greater than 0, k being an integer greater than or equal to 5, there exists a small delta, which is positive, that if a time periodic force F with time period capital T greater than 0 satisfies, it wouldn't really matter, but that's just to restrict it. Because if it was negative, it would be absurd, but it would just match the same period to the forward. Do I know about distribution derivative? No. All right, magnitude of F, the time periodic force, subscript C within the real numbers, also this B space intersected with the H dot space. Oh my god, Besov space, there we go. And the inhomogeneous Sobolev space above. Yeah, I mean, color, is this going to be a fool's errand for me to even attempt to look at this? Existence of the time periodic solution. There exists multiple time periodic solution, rho t, vt, theta t, satisfying the following. So rho t, the magnitude of the distances between the time periodic solution value and the like essentially steady state, I think, is what it's going for at infinity. And v sub t has a v sub infinity of 0. So we've already established that above. It's going to stop moving eventually, essentially is what it's going for, I think. Must be less than or approximately equal to delta. Stability, if initial data rho 0, v0, theta 0 satisfy this thing. Then there exists a unique global solution. probably seen distributions show up in Fourier transform when you want to compute the Fourier transform of 1 or sine x. This will be given in terms of the so-called delta function. I have definitely seen the delta function, specifically looking at the Laplace transform. And we talked about the green function that showed up because I was trying to solve, I think I was manually trying to solve the Laplace transform of something, or inverse Laplace transform of something. So green's function showed up, and I was like, what the F is this? So we looked at it for a bit, tried to figure it out. That worked moderately well. Okay, it's an example of a distribution. It's fair. I thought this was trying to be like literally the delta of delta epsilon stuff where you're just picking like, give me a small value. Okay, so existence makes sense, right? So we're saying like that is what this is. Yeah, this delta is just pick a small value. Because here it's saying there will exist a time periodic solution, unique time periodic solution, as long as the amount that we get, the eventual magnitude between the time periodic solution, the unique theoretical unique time periodic solution, and the value we're supposed to get at infinity is going to be ever smaller given, I guess, talking about a limit as like the rho sub n starts approaching infinity. It shouldn't use n. Whatever. Oh, Sobolev space. Okay, yeah. The other delta, not this delta, but the other delta, which is a function, not this delta, which is constant. I got you. Stability. So if the initial data Oh, yeah. Okay. So if the initial location is within some infinitesimal amount of the final solution. So we strategically pick a particular value, which is going to be ever and ever closer to what we think is the eventual solution, the eventual stable point, rho infinity, 0, theta infinity. We pick a value, rho 0, v0, theta 0, such that we could move that thing ever and ever and ever closer to what turns out to be, right? Rho infinity, 0, theta infinity. And we get closer and closer to that thing, then yes, it will be considered a stable point. In general, distributions a linear map L that takes a function, gives you a number. Yeah. For the example, Dirac delta distribution, you simply take a function and evaluate that function at x equals 0. That's nice. Then there exists a unique global solution, rho v theta of 1, the system, in 0 to infinity by R3, with initial data rho 0, v0, theta 0, and has the property that the magnitude of the distances between rho and rho infinity, v and 0, and theta infinity are going to then be less than or approximately some tiny value, delta. In addition, for any epsilon, greater than 0, if delta is greater than 0, is sufficiently small, and our initial distances do you know what the L space is? The distances between rho 0 and rho sub t of 0, v sub 0 and v sub t sub 0, and theta sub 0 and theta sub t of 0 are within our LP for some p between 1 and 2 inclusive. Then we have time decay estimate given here. F is in p integral function. So if F is in L super p if int n space F, is that literal raised to the p? Is finite. Yeah, literal powers. Okay. We note that the decay rate obtained in 4 coincides with that of the heat semigroup. Employment Bezov space is motivated by the need to control slow spatial decay of time periodic solution. Indeed, since the diffusion terms mu times delta v plus mu prime times the gradient of divergence of v and kappa over c sub v times delta theta are classified as elliptic operators. The spatial decay orders of the velocity v sub t and temperature theta sub t minus theta sub infinity are expected at most O of 1 over absolute value of x, as absolute value of x tends to infinity, respectively, by comparing the spatial decay order of Newtonian potential in R3. Slow decay suggests that the time periodic solution does not belong to L2 in R3. Previously, Ma, Ukai, and Yang derived the decay estimate 3 in dimension n greater than or equal to 5 by combining the analysis used in the linearized semigroup to the constant state rho infinity 0 theta infinity, and the energy estimates in H super n minus 1, where n is within the integers greater than or equal to n plus 2. In their work, the dimensional assumption n greater than or equal to 5 is used to control the L2 norm, L squared norm, of the time periodic solution. To establish the decay estimate of the perturbation at dimension n equals 3, we develop the framework of perturbation analysis in the function spaces Bezov. Is the Bezov space doing a square root? Or is that something completely different with the 1/2 there? Subscript 2 to infinity. Usually restrained to p between 1 and infinity. And for p equals infinity is simply defined space of bounded function. I mean, can't be greater than or less than or equal to infinity, but I get your point. Intersected with h dot k. K is going to be greater than or equal to all integers greater than or equal to 5, which spaces allow for slow decay, such as 1 over absolute value x. In addition, spaces Bezov intersect H have good compatibility with the energy method developed by Matsumura and Nishida for constructing strong solutions to the compressible Navier-Stokes-Fourier system. Since the spaces are L2 base space, here we mentioned that the space given with H3 was used for perturbation analysis of stationary solutions to the isentropic compressible Navier-Stokes equations in 3. Difficulty in proving Theorem 1.1 arises from convection terms in the Navier-Stokes-Fourier system. I mean, mood. Since the spatial decay order of the time periodic solution is expected to be at most O of 1 over absolute value of x, the convection term v dot gradient v appearing in the Navier-Stokes equations is expected to exhibit the same spatial decay order, O of 1 over x cubed, as the viscous term mu times delta v. Thus, we need to treat the convection terms carefully in order to prove the existence of a time periodic solution and to derive the decay estimate for its perturbations, even if the external force is small enough. For this reason, Yamazaki and Tsuda transform the convection term v dot gradient v to the divergence forms, divergence of v. Oh, nuts. I used to know what that was. Alright, so for all the crazy vector products we have, is that a... Boo! Your PowerPoint stinks. It's got too many words. I'm not going to call this person out. Nope. Prototype example of distribution given function f, defined associated distribution to f as capital F of g equals int n space. The function g are called test functions for your analysis usually used. Fast decaying smooth function, for example, Gaussian as test functions. It's fair. Hey, there we go. Outer product. There we go. Right, so outer product of two vectors is just going to be an m by n matrix based on the number of rows and columns in each, where we're just going to make all of the columns into the U matrix and then all of those columns are going to be multiplied by individual elements in V. So here we have our standard U1, U2, U3, etc. to UM, all multiplied by V1. Then the next one over is a copy of U, so it's U1, U2, U3, all the way down to UM, all multiplied individually by V2. So M by N matrix, really big. Okay, so the outer product of V by V is going to be, V1 squared followed by V1 times V2 with V1 times V3, V1 times V4, V2 times V1, V2 squared, V2 times V3, etc. So all of this is going to be a diagonally symmetric matrix, given that it's V outer product with itself. And then we do the divergence. I don't remember what the divergence does, but that's fine. And divergence of rho times V outer product with V, respectively, by using the mass conservation law. Then establish an a priori bound for the solutions to the Navier-Stokes equations. However, in Navier-Stokes-Fourier systems case, the additional convection term v dotted with gradient theta, and the non-divergence term theta times the partial with respect to theta of p over c sub v rho times the divergence of V appear in the equation of the temperature in number 1. In section 3 below, to establish a priori estimate in the homogeneous Bezold spaces, we shall introduce the modified energy functional, capital epsilon, is equal to all of that. P1, P2, Q1, Q2 are all given here. By introducing the modified energy functional, let delta equal the difference between rho and rho infinity. M is going to be equal to rho V, density times velocity. And eta is the difference between theta and theta infinity. And equation 1 is transformed into the following systems of equation. H1, H2 are higher order terms, except for external force terms and higher order terms. All nonlinear terms in 6 are written in divergence forms or potential forms. This transform is used to establish a priori estimates for initial value problem 1 in proofs of propositions 3, 5, and 3, 6 below. Proof of time decay estimate 4 is inspired by the strategy used in 3. Proof will be carried out by writing the perturbation U equals the following in Duhamel form. U of t is equal to e to the t capital A times U of 0 plus the integral from 0 to t of e to the tau A times phi of t minus tau d tau. That is, that looks very similar to another Laplace transform, but I don't think it's quite the same there. Hey, Stookie. Been hard at work. Hardly working. I'm just reading papers, man. Hey, Zach, welcome back. Yeah, no, we were doing some nice history stuff back here with Euler doing spherical geometry, and now we've got to the stability of Navier-Stokes-Fourier systems, which is way beyond my pay grade, but nonetheless, it's fun to sometimes look at some stuff. I mean, it is fun to sometimes look at some stuff and be like, imagine if I actually understood what this meant. Where t is greater than 0, A is this big giant matrix here. Phi denotes the remainder terms that contain linear terms such as the following. Key step of the proof is derive a time-weighted estimate for Duhamel integral using the supremum of this stuff. Epsilon greater than 0. S sub 0 is between negative 3/2 and 1/2. S sub 1 is max of S sub 0 is 0. Max of, S is between the max of S sub 0 and negative 3/2 plus epsilon to 3/2 minus epsilon. By virtue of rewriting the convection term as the divergence form, bilinear estimate of lemma 2.5 below allow us to prove the estimates such as this given here. I wonder if there was a bet as to who could create like a sine function inside their equations. So that if time periodic solution is sufficiently small and high frequency norm, h3 of the perturbation, h dot of 3 of the perturbation is well controlled, then the linear operator divergence of v sub t outer product with dot can be treated as a simple perturbation of the operator A. Time-weighted estimate high frequency norm is proved by using the energy method of Matsumura and Shida, proposition 3a below. Alright, so I don't think we're getting anywhere near. So we'll probably just fold on this one, because there's way more stuff in here than I could possibly understand without doing a serious amount of research. So we'll kick that one off to the side. I think we did look at this before. Maybe. Largest common subtree of two random trees. Maybe not. Short time estimates of solutions under certain conditions. The main theorem, right? Large time behavior of perturbations around time periodic solutions to Navier-Stokes-Fourier systems in three-dimensional whole space. Time periodic solution exists when a given external force is small enough. We derive time decay estimate of perturbation under the assumption that initial perturbation is sufficiently small. Time-space integral estimate for the linearized semigroup around constant state in Bezov spaces is efficiently applied in the proof. I hope you understand, because I definitely don't. Or understand enough, perhaps. Okay, so Omer Engel, Kalin Atmanchuk, Anna Bradenberger, Seta Donderwinkel, and Robin Kanfer. Abstract. We study the size and structure of the largest common subtree, LCS, between two independent Bian-Aimé trees conditioned to have size n. When the trees are critical with finite second and 2 plus kappath moment, respectively, for some kappa greater than 0, we prove that the LCS has size of order root n and is approximated by a length of tree paths meeting at a central node. Moreover, we show that the largest common subtree between two critical independent Bian-Aimé trees with size n and finite second moments may be much larger than root n, implying our result is tight. We also pose a number of open questions and suggestions for future research. Maybe we did read this. This proof is tight. For trees T, T prime, and T double prime, say that T double prime is a common subtree of T and T prime if T double prime is isomorphic to a subtree of both T and T prime. The size of the largest common subtree of T and T prime is denoted by LCS TT prime. The purpose of this paper is to study LCS when T and T prime are two independent random trees. Natural setting is that of Bian-Aimé trees, conditioned to have size n. The following theorem is a less detailed version of our main result, theorem 1-2. Let tau sub n and tau sub n prime be independent critical Bian-Aimé trees, conditioned to have size n, whose offspring distributions have finite 2 plus kappath for some kappa greater than 0 and a finite second moment, respectively. Then there exists a finite random variable x greater than 0, for which n to the negative 1/2 times LCS of tau n prime goes to x, where we have d as the n going to infinity anyway. And d. Yeah, I don't see it. Anyway. We remark that we view trees just as just graphs with no additional structure as vertex labels or plane embedding, even though in our proofs we use the Ulam formalism for trees wherein vertices have a natural order. In theorem 1.3, we show that this result is tight in the sense that having finite second moments for both offspring distributions is not sufficient. Our main result is theorem 1.2, which relates the limit x to the scaling limits of Bian-Aimé trees. To state that result, we need some critical definitions. Let mu be mu of k, where k is greater than or equal to 0, and mu prime be mu prime of k, where k is greater than or equal to 0, be two critical and non-trivial offspring distributions, meaning that one is equal to the sum of all k times mu of k, which is equal to the sum of all k times mu prime of k. Right? So Department of Mathematics, University of British Columbia. Okay, just where they're all from. Bernoulli Institute, nice. Groningen. And McGill, British Columbia. MIT, nice. 2010 mathematics subject classification, keywords and phrases, blah, blah, blah. Also known as Galston-Watson trees or family trees of branching processes. Moreover, we can assume that mu and mu prime have finite second moments. So sigma squared is defined as the sum of all k's, k minus 1 squared times mu of k must be less than infinity. And also sigma prime squared is going to be defined by the sum of all k's as parentheses k minus 1 squared times mu prime of k is less than infinity. Let's denote by tau and tau prime two independent Bienname trees with respective offspring distributions mu and mu prime. Formal definition of Bienname trees is given in section 2. Good. We'll hereafter only consider n for which p of number of tau equals n is greater than 0, and p of number of tau prime is equal to n greater than 0. Then for any such n, denote by tau n and tau n prime two independent Bienname trees with offspring distributions mu and mu prime respectively, and conditions to have size n. We view tau n and tau n prime as compact metric spaces equipped with their distance graphs. No, graph distances. For a metric space E equals ED and lambda greater than 0, we write lambda that is multiplied. Okay, so lambda times E is going to be equal to E lambda D for the metric space obtained by rescaling the distances, by a factor of lambda. It's now well known that 1 over root n times tau n, 1 over root n times tau n prime, as n goes to infinity on d, distance, goes to 2 over sigma times fancy t, two independent Brownian continuum random trees, CRTs. Brownian continuum random trees. Okay, so 2 over sigma times our first Brownian continuum random tree, comma 2 over sigma prime times big T prime, fancy T prime. More precisely, if E equals E sub s, where s is between 0 and 1, inclusive, is a standard Brownian excursion, then fancy T and fancy T prime have the same law as the quotient metric space of 0 to 1 inclusive, induced by pseudo-distance D sub E, defined as follows. So S1, S2 must be between 0 and 1 inclusive, and S1 is smaller than S2 if different. D sub E of S1, S2 is equal to E sub S1 plus E sub S2 minus 2 minimum, 2 times the minimum of E on S1 to S2 inclusive. Okay. Finally, we introduce our limit quality for any two compact matrix spaces E equals ED and E prime equals E prime D prime. Set phi of EE prime to the supremum of half the distance between, the sum of half the distance between all of the individual pairs that we get, where x1, x2, x3 are in E, x1 prime, x2 prime, x3 prime are in E prime, such that the distance of all x sub I, x sub j are equal to the prime distance between x sub I prime and x sub j prime for all i's and j's. So there's like a distance mapping that can be done, and those mappings are the same, I think. If I'm wrong, please correct me. All right, we should wrap here, though. I need to get up early in the morning. Got to run over to the old house, grab the trash and the recycling out of it, grab the paint out of it, grab the toilet brushes out of it, go toss them in my car, and then hand over the keys, because we'll be out of there officially as of tomorrow. All right. Dr. Gold's in the house today. So let's go over and see Dr. Gold. Provided that we can. I've been denied a few times recently. It's like, oh. Alright, so see you all over there in a second. I will be back likely tomorrow to do our gamey type stuff slash clean up a little bit in here. So we'll probably be doing blueprints again, and I gotta get some more stuff put on the YouTube channels. Right, YouTube channels. Just in case anybody has not seen this yet. So we are at Obi-Wan Pez for our gaming stuff, and at nsimplexpachinko6542, or if you just search nsimplexpachinko, it will show up on YouTube as me, this guy. Have a beard and like do mathy stuff. So you'll see it. I have subjects for basically everything from basic algebra all the way up through differential equations, a little bit beyond naturally as we're doing some of this research stuff here. Not much. But it is, at the moment, pretty much all unedited streams. So yeah, there's some fun stuff in there. Someday we might actually get Who's It's to work properly. This is going to take us over there. So thank you all, everybody. My name's Obi-Wan Pez. This is nSimplex Pachinko.